Okay, so now we're starting part 2 of these notes. So let's go through and let's talk about some properties of log functions. Let's go down and let's look at these pictures. So you can see here, this graph right here is the graph of a log. And here your base is a fraction. It's between 0 and 1. So this would be like log base 1/2 of x or log base 1/3 of x. And it would look like this. So it would be like a decreasing function. Its inverse, which is y equals a to the x, the inverse, the kind of corresponding exponential function that we dealt with in the last unit, y equals a to the x, where again the base, the a, is a fraction between 0 and 1. You'll remember that that one was a decreasing function like this. And here, going with the base being greater than 1, that's an exponential function that looked like that. We graphed those. And if it's a log function, where this would be like maybe log base 3 of x, it looks like this. So notice here in the exponential function, the x-axis is the asymptote. In the logarithmic function, the y is the asymptote. All right, so let's kind of fill in some blanks here. So for a log function, log base a of x, the domain will be from 0 to infinity. We already looked at that, and the range is all real numbers, so we've already written that. The x-intercept right here is 1, 0. Remember, for exponentials, it was 0, 1. And there is no y-intercept. Remember, for exponentials, there was no x-intercept. Again, they're inverses, so it's opposite. The y-axis, which is x equals 0, is a vertical asymptote. Remember, we had horizontal asymptotes when we had exponentials. The logarithmic function is decreasing, so decreasing if x is between 1 and 0, and increasing, not x, a. Let's use the right variable, your a, your base, and increasing if a is greater than 1. The graph of f contains the points. Well, it'll contain the point 1, 0. You can see that they contain the point 1a. Oh, I'm sorry. Actually, let me see. This is the log. It's going to contain the point a1. Knew that didn't seem right. And it's also going to contain the point 1 over a negative 1. So that would be this one right here. You can see that in the picture. So remember, this was the log function, and this was the log function. So that's where we're taking those points from. And the graph is smooth and continuous with no corners or gaps. Then just quickly down here, they talk about a natural log graph. Remember, the natural log function really just means log base e. So that's all it means, is that that base is going to be e. So since e is about 2.718, we learned that in the last section, this would be the graph of y equals the natural log of x. And right here is the graph of y equals e to the x. So I also wanted to quickly point out, I've said a couple of times that logs and exponentials are inverses of one another. Notice for each one of these pairs of graphs, there's symmetry with respect to the line y equals x. Here, that's why they have that drawn. Here and here. And remember, that will always be true if you're talking about graphs of inverses of one another. All right, so let's go ahead and let's do this graph. So as I look down here, it says the first thing they want me to do is to state the domain. So I'm going to go ahead and I'm going to state the domain. Again, I know that I need this to be a positive number, so that means x minus 1 has to be greater than 0. Oops, did I accidentally? Oops, I turned 2 pages. Has to be greater than 0, which means x has to be greater than 1. So my domain is everything from 1 to infinity. Okay, so now it says from the graph, determine the range. Well, if I know that my domain is from 1 to infinity, I hope you understand that that really means that there is a vertical asymptote there. My range will always be all real numbers for any logarithmic function. And in this case, my vertical asymptote is x equals 1. You can get that by just taking this and setting it equal to 0. So now it says find the inverse of the graph. So let's talk about how we find the inverse. We're going to use the exact same method we did in a previous section. So I have here y equals 3 times the natural log of x minus 1, and I need to find the inverse. So the first thing I'm going to do is get the log part alone, so that's going to give me, nope, I lied. First thing you're going to do is flip the x and the y. Remember our steps. And then we have to solve for y. So if I'm going to solve this equation for y, the first thing I'm going to do is get the log part alone. So that would be x over 3 equals the natural log of y minus 1. Now remember, natural log really means e, a base of e. So now I'm going to use my definition, and I'm going to say e to the x over 3 power is equal to y minus 1. Again, e to the x over 3 power equals y minus 1. And then if I solve for y, I'm going to get e to the x over 3 plus 1. And then, of course, I'm going to put that in my correct function notation, which would be f inverse of x equals e to the x over 3 plus 1. And that is the inverse. So I'm going to go ahead and I'm going to write that down here. So now let's go ahead and let's graph these. So what I'm going to do, because this is easier to plug values in for x, I am going to plug values in for x right here and plot this. So if I make myself a chart, well, if I plug in x equals 0, so e to the 0 power is 1. 1 plus 1 is 2. If I go ahead and plug in, I don't know, let's plug in 2. I would then do e to the 2/3 power. And I'm just using my calculator. So e to the 2/3 power plus 1. That's going to give me 2.9. I'm going to plug in a 4. So again, that would be e to the, what would that be, 4/3 power? Plus 1, that's going to give me 4.8. Let's go ahead and let's plug in a, maybe a -2. If I plug in a -2, so that would be e to the negative 2/3 power plus 1. I'm getting 1.5. So let's see what's happening here. So 0, 2. So again, I'm graphing the inverse, which is an exponential. 2, 2.9, which is about right there. What else did I have? 4, 4.8. And negative 2, 1.5. So now, remember that if this was a vertical asymptote for the log function, then that means that this is a horizontal asymptote for its inverse, which is an exponential function. So you can see my graph looking like this. And this is f inverse. Now I'm going to flip the points that I graphed to help me find the inverse graph, which is this log graph. So instead of 0, 2, I'm going to plot 2, 0. I'm going to plot 2.9, 2. I'm going to plot 4.8, 4. So 4.8, 4. It's about right there. And I'm going to plot 1.5, negative 2. So you can see that guy's kind of going like that. Notice if I were to graph this line, you would see the symmetry. Now, you can plug in with your calculators points for here for x, and then get your f of x if you wanted, and then flip those points to graph the inverse. That's totally up to you which one you want to do. I just think this was a little bit easier. All right, so if we go down here, you can see now we already had natural logs. Now we're going to talk about what we call a common logarithm. A natural log, remember, was a log base e. A common logarithm is a log base 10. And when you look at the LOG button on your calculator, that is a common log. It is log base 10. And when we have a log base 10, we assume that 10 is there, so we write it just as log of x. Okay? So if you look, y equals log of x if and only if 10 to the y power equals x. So there's an understood 10 here. And if I use our definition, 10 to the y equals x. So natural logs are base e, common logs are base 10. So I'm going to stack my papers again. Let's go ahead and let's graph this one very similarly to what we did. So first of all, you can tell by looking here that my domain is going to be from negative 2 to infinity. So I'm just writing that down there, which means that there's going to be a vertical asymptote at negative 2, which, by the way, means for the inverse, because it says I have to also graph my inverse, there's going to be a horizontal asymptote at negative 2. So you know what? I'm just going to throw that right in there. Okay, so why don't we go ahead? I am going to find the inverse first. So again, if I take this function and if I flip the x and the y, it's going to be x is equal to negative 2 log of y, whoopsie, y plus 2. So now before I have to change it to an exponential, I have to get this alone. So I'm going to divide by negative 2. I'm now going to remember that this has a base of 10. So if I use my definition, it would be 10 to the x over negative 2 is equal to y plus 2. So I'm solving for y. So y equals, or f inverse of x equals 10 to the x over negative 2 minus 2. Here is my inverse function. Okay, so once again, to graph, what I'm going to do is I'm going to plug some values in here, and then I'm just going to flip them to do my log graph. So if I plug in 0, 10 to the 0 power is 1, and 1 minus 2 is -1. Okay, if I plug in, let's plug in 2, that would be 10 to the -1, which is 1/10 minus 2 is -1 and 9/10. If I plug in 4, that's going to be 10 to the -2, which is 1 over 100 minus 2, and 1 over 100 minus 2 would be -1 and 99 100ths. So you can see we're getting really, really close to -2 there. Let's just quickly plug in -2. That's going to give me 10 to the first, which is 10 minus 2 is 8. So again, these are for the inverse. So I'm going to go ahead and I'm going to plot 0, -1, 2, -1 and 9/10, 4, -1 and, yeah, so it'd be right down there, and then -2, 8. 1, 2, 3, 4, 5. So that's this graph right here. So that is the inverse. That's my F inverse, which is a log function. Notice because it's a -2, that's why it's going down like this. And now if I go ahead and if I flip my points, so -1, 0, -1 and 9/10, 2, so -1 and 9/10, 2. And then how about 8, -2? 1, 2, 3, 4, 5, 6, 7, 8, -2. So that guy is kind of going kind of like that. You can barely see it. You can see that they're symmetric. You might want to practice with your grapher. Plug those into your grapher. I think that will help. So just really quickly, if I want to fill these in from the graph, for the function, which is my f of x, my range is obviously all real numbers. It always will be. And there's a vertical asymptote of x equals -2. I found the inverse. It's right here. And then I went ahead and I graphed them. And again, for this one, you would just flip the domain and the range of this one.